In this second part of gas chromatography, we will continue seeing the rest of chromatograph components. First, how the chromatograph achieves temperature control, and the most employed detectors coupled to gas chromatography. Then, we will explain what sample derivatization means, why and when is applied. Finally, common applications for analytical qualitative and quantitative purposes will be reviewed. The temperature control is performed in an oven. The oven in a gas chromatograph is a heating system that works with air circulation inside a cavity. The characteristics of a good oven must be to have a wide range of temperatures to cover a great number of compounds to be analyzed. The temperature must be uniform inside. It's desirable to get a stability of plus minus 0.1% or no more than 1 Celsius degrees difference between different parts of the oven. To have easy access to the column to put it on and take it off, and to have fast heating and cooling so as not to extend the analysis too much. Nowadays, the instruments are equipped with microprocessors which control and monitor the temperature during the analysis. Temperature optimization is essential to obtain a good separation in gas chromatography. An increase in temperature increases the vapor pressure of the components and consequently the migration rate, resulting in a reduction of the retention time, but also peaks resolution. This loss of efficiency is because working under isothermal conditions with mixtures of components with different volatilities, the more volatile components leave the column earlier and the less volatile ones are retained longer, resulting in peak broadening. This is represented in the upper left figure. On the other hand, if we work under isothermal conditions at higher temperature, the first compounds leaving the column close together and don't separate properly. Look at the bottom left figure. In either case, a good separation has not been obtained. The solution would be to carry out a better separation by applying a linear rising temperature program, allowing the separation of the mixture of compounds in the shortest time with good resolution. The equation describing the dependence of the retention time with temperature is shown in the blue box, where uppercase T is the temperature in Kelvin and lowercase t is time in minutes. The important point in this equation is that temperature and retention time are inversely proportional. The above statements are shown in this practical example, where we can precisely see the influence of temperature in the separation of 9 compounds. A temperature too low, 45 degrees, leads to a bad separation as the 5th compound is too retained, then almost undetectable. And the situation is even worse for compounds 6, 7, 8, and 9 not registered in this chromatogram. Increasing temperature up to 145 degrees provokes overlay of the 4th first compounds. Quantification of compound 8 is not possible, and even the 9th component has not come out after 30 minutes. Then, an increased temperature program is mandatory, starting at 30 degrees to elute highly volatile compounds and finishing at 180 degrees for dilution of the less volatile. In these conditions, all compounds are well resolved and its quantification is possible. The last essential part for a chromatograph is the detector that gives the analytical response for the solutes. The detectors used in gas chromatography must have a few characteristics, such as Rapid response. Ideally, gas chromatographic peaks last 1 second or less. High sensitivity to small solutes concentration. Linear response over a wide range of concentration, which means high dynamic range. And stability over time. There are two types of detectors. Universal, that give a uniform response for a wide variety of chemical species, or alternatively selective, that give analytical response towards few classes of solutes. In the case of complex samples, a selective detector will be more appropriate, since by responding only to a limited group of compounds, the chromatograms are simplified. There are several gas chromatography detectors, covering a wide concentration range, from milligrams to picograms. Of all of them, 5 have been selected as the most widely used today, and are summarized in this graphic. They are presented based on their sensitivity. We are going to discuss each of them separately to explain the basic principle of operation. Thermal Conductivity Detector, TCD. The term thermal conductivity refers to the ability of a fluid, in this case the carrier gas, to transport heat from a hot zone to a cold zone. The higher the thermal conductivity, the faster the heat transport. It's a universal detector that responds to all compounds since it's based only on variations in the thermal conductivity of a gas depending on its composition. However, it's restricted to some kind of compounds, as we will see in the next slide. The figure shows a typical TCD configuration consisting of 2 cells, each containing 1 hot wolframium filament. Carrier gas continuously flashes through the reference cell, while the effluent from the column passes exclusively through sample cell containing carrier gas plus analyte. This detector senses changes in the thermal conductivity of the column eluent and compares it to a reference flow of carrier gas. Since most compounds have a thermal conductivity much less than that of the common carrier gases like helium, hydrogen, or nitrogen, when an analyte elutes from the column, the effluent thermal conductivity is reduced, and a detectable signal is produced. The TCD consists of an electrically heated filament in a temperature-controlled cell. Under normal conditions, there is a stable heat flow from the filament to the detector body. When an analyte elutes and the thermal conductivity of the column effluent is reduced, the filament heats up and changes resistance. This resistance change produces an electrical signal, which is conveniently amplified and recorded. Since the detector responds to changes in the thermal conductivity of the gas flow, it's desirable that the conductivities of the solute and the carrier gas be as different as possible. The thermal conductivity of a substance is inversely proportional to the molecular mass, so the lower the molecular weight of the carrier gas, the greater the response. Therefore, hydrogen and helium are often used since they have higher thermal conductivities and produce higher signals compared to nitrogen, for instance. In this same way, the lower the thermal conductivity of the analyte, the larger the conductivity difference with the carrier gas, and then the higher the response. In general, the changes produced are very small, so they must be amplified to be able to quantify the signal produced. The main disadvantage of TCD is that sensitivity is highly dependent on the carrier gas flow rate. This detector is generally employed for the separation and quantification of compounds that don't generate a signal in other detectors such as permanent gases, nitrogen, ammonia, carbon dioxide, methane, and low molecular weight hydrocarbons. Flame ionization detector, FID. It's generally employed for organic compounds since it's highly sensitive to CH bonds, so we can say it's a real universal detector. The gaseous stream leaving the column enters the flame of a small burner fed by a mixture of hydrogen and air, where the compounds are pyrolyzed, and then forming ions and charged particles which create an electric current. A polarized cylindrical collector is placed above the flame in order to collect the ions generated. The ionic current established between the tip of the burner and the collector electrode is measured. In the total absence of organic compounds, not many ions are produced in the flame, so the current is practically null. However, when analytes come out from the column, ions will be formed in the flame being conducted by means of an electric field applied to a collector, and the electric current produced will be measured. The more carbon atoms the molecule has, the more fragments will be produced, and the more current the detector measures. The response of this detector depends on the reactions taking place in the flame. In general, it's proportional to the carbon atoms number. However, the presence of heteroatoms decreases the response factor. It has higher sensitivity than thermal conductivity detector. However, it's not useful for detecting small compounds such as carbon dioxide, nitrogen oxides, carbon disulfide, water, ammonia, methane. For such compounds, TCD is the most useful, as we have already said. The advantages of flame ionization detectors are that they offer high sensitivity, high stability, and an exceptionally high linear dynamic range, together with great simplicity of use. All these features have made this detector the most widely employed in gas chromatography. On the other hand, the main disadvantage is not useful for small molecules and molecules with heteroatoms, as we have also said. Nitrogen phosphorus detector, NPD. It's a modification of the previous detector, FID, in which the only difference is that it contains a salt or ceramic of an alkali metal, usually rubidium, close to the flame. The presence of the salt causes the flame conductivity to increase significantly and specifically when compounds containing nitrogen, phosphorus, or halogens pass through the detector. Hence, it's a selective and sensitive detector for compounds and molecules containing these elements. The main disadvantage is its relatively low stability due to the alkali element's loss over time. In addition, the selectivity is highly dependent on parameters such as temperature, flame shape and size, flame air content, alkaline salt composition, and detector geometry. Therefore, the handling of this detector is difficult, and the response optimization is tedious. It's little employed in comparison with FID. Electron capture detector, ECD. The electron capture detector is probably the second most widely used after FID due to its exceptional sensitivity. It's an ionization detector that measures the decay of an electric current between two electrodes, an anode consisting of a plate of a radioactive material, nickel-63, tritium, iron 55, and a cathode. The radioactive material emits beta particles, which ionize the carrier gas, nitrogen or argon, and give rise to a plasma containing free radicals, electrons, and positive ions. The electrons are attracted to the anode, establishing an electrical current. When a compound containing electronegative atoms arrives to the detector, some of the electrons will be captured by these atoms, causing a decrease in the current traveling to the anode. This decrease is proportional to the concentration of the electrophilic species present, and after amplification, give the corresponding signal. Then, this detector is mainly used for molecules containing electrophilic groups, like halogens, conjugated carbon groups, nitrile groups, nitro compounds, and organometallic compounds. On the other hand, it doesn't detect hydrocarbons, alcohols, and ketones. The handling of these detectors is not simple, since their response can be very variable depending on the experimental conditions, polarization potential, temperature, carrier gas flow rate, etc., affecting not only their sensitivity but also their selectivity and their linear dynamic range. Additionally, the presence of radioactive materials can be harmful for the user. Mass spectrometry detector, MSD. It's a very powerful tool currently available for the identification of the different components of a complex mixture. For this reason, it's the most widely used detector coupled to a gas chromatograph, together with FEED. The figure shows the components of a mass spectrometer detector at the outlet of the gas chromatography capillary column. There is a connection to a transfer zone, so-called interface, to the mass spectrometer. Inside the detector, there is a source generating the ions of the compounds that are eluting from the gas chromatographic column. The ions are focused towards the vacuum zone by means of lenses. Then, separated in the mass analyzer, and an electron multiplier amplifies them for recording and data processing. The main aspects concerning coupling, gas chromatography, and mass spectrometry will be discussed in Unit 5. The table on the slide summarizes the most important characteristics of all detectors mentioned in this unit. Among the data included is the compounds detected by each one, the detection limits achieved, and the dynamic range. Derivatization is defined as a chemical process by which the initial analytes of a sample are transformed into other compounds by chemical reactions. Derivatization can be applied with several objectives. The main ones in the specific case of gas chromatography are to improve the thermal stability of the analytes, as this is a main requirement for the compounds to be separated by gas chromatography, or to improve chromatographic resolution to avoid overlaps between various compounds present in the sample, or to improve the sensitivity and selectivity of an analyte, or to reduce compounds' polarity, for example, converting ionic species into neutral ones to be compatible with gas chromatography. This step of a chromatographic method can be performed before, after, or in the column itself. Some typical examples of derivatization reactions are esterification of carboxylic groups, known as Fischer reaction, acylation and alkylation, Williamson reaction, among others. Applications of gas chromatography. The compounds to be separated by gas chromatography must comply with: they must be volatile or thermally vaporizable, they must have chemical stability at working temperature, they must have low molecular weight, less than 300 Daltons, and they must be compounds in their non-ionic form or compounds without hydrogen bond-forming groups. If this is not the case, these compounds must be derivatized, as explained in the previous slide. As we have said in Unit 3, chromatography is employed with identification purposes, qualitative analysis, but also to quantify the separated target compounds, quantitative analysis. For the first case, qualitative analysis, it's possible to identify species in an unknown sample using retention times as a source of information. Or we can determine the identity of the compounds through the structural information provided by specific detectors such as mass spectrometry. The retention time is not always the ideal parameter for the identification of a compound since it depends on the temperature of the column, the flow rate of the carrier gas, and the thickness of the liquid stationary phase film, among others. Therefore, in some cases, in gas chromatography, a parameter that does not depend on these factors can be employed, which is the Kovács retention index. However, this index has the limitation that it can only be calculated for homologous series of N-alkanes. Kovács retention index establishes a linear logarithmic relationship between the capacity factor K and the number of carbons for such an homologous series of N-alkanes. The mixture is injected into a column maintained in isothermal regime, and the corresponding chromatogram is obtained. The graph of the number of carbons versus logarithm of K is plotted, having a linear dependence as shown in the slide. The slope of this line depends on the column used and the chromatographic conditions. In such a way, it's possible to calculate the number of carbons of an unknown molecule that elutes between other two known compounds, or we can also predict the retention time of a compound of the series. This index is often used to identify aromatic compounds and substituted compounds. They are also useful for compounds with double and triple bonds. In any case, this is more an estimation methodology, which is mainly employed in the petrol industry. Gas chromatography can also be employed with quantitative purposes by transforming the analytical signal of the detector into concentration. For this, it's necessary that the detector has a linear operating range that covers the expected concentrations of the analytes. We could apply an external calibration. In such a case, we would construct the linear relationship between peak areas and concentration. But it's more frequent the use of an internal standard calibration in gas chromatography. In such a case, the linear plot represents the ratio of analyte areas with those of internal standard versus the radius of analyte and internal standard concentration. We get the equation in the slide. As we explained in Unit 3, the internal standard is always added at a fixed concentration, and it's a compound that has similar characteristics to the analyte for the detector. It's mandatory that the internal standard retention time be different than the retention time of the analytes to be measured. In other words, the internal standard must give a totally resolved peak in the chromatogram. The quantification in GC can also be done by calculating a response factor without needing to make a calibration curve. In this case, the response factor is calculated with the signal of the analyte standard and the internal standard as shown in point 3 of the slide, strong blue box. Once the response factor has been calculated, the sample with a known analyte concentration is measured by applying the formula in the light blue box. Of the three possibilities, the second and third are mostly employed in gas chromatography. Some application areas with concrete examples where gas chromatography separation is widely used are shown in the slide.